Hello, friends. Welcome to episode 11 of Kermit GNC. So, today we will work on building Actuator Dynamics into our model, and very soon we are going to start putting things together to connect our model with a potential FlightGear simulation or visual interface. But that's coming up, spoiler alert. And if you have not checked out the previous episodes, I have the link on the description below. Definitely check those out in order to understand what we are doing now, because we are building layer by layer. So episode 11, Actuator Dynamics. Today we will do Actuator Dynamics insertion into the pilot command. So the actuators will actually in a way influence the surface deflection with some delay and rate limitation. I will talk more about it. So we will configure actuator. We are going to use the first order servo lag function, which is a pretty simple function that captures the essence of actuator at a very foundation level. And we will, after that, we will achieve control bias architecture, which we have already done. Control bias architecture is nothing but the fact that we separated our pilot commands away from the trim algorithms or trim offsets. That is what is control bias architecture. So, we created that bias separate from the pilot commands. And with the actuator, we will achieve control actuator dynamics. So after this episode, those two will be done. And we will try to make a flight dynamics output subsystem, which will come in handy when we start connecting things to FlightGear. So let's get started. I will start the session with a little bit of explanation as to why actuator dynamics in the entire flight simulator model. So aircrafts have So you know how in earlier days, aircrafts used to just move the stick and then the control surfaces would just move because of cables, pulleys, and push rods, things like that. But over time, as aviation evolved, aerospace evolved, we have started replacing those cables, pulleys, and push rods by things like electric servos, hydraulic actuators, electrohydraulic actuators, fly-by-wire computers, right? Fly-by-wire is a very big skill set to have in terms of industry skills. If you look up like most of the jobs around this guidance, navigation, and control side, this is a key word they mention on the job description as to, do you have fly-by-wire experience? So this is what they are talking about. Fly-by-wire is definitely when a pilot moves the stick, the control surfaces are not going to move magically, but there is going to be a fly-by-wire system or computer in between, which means when a pilot gives command, it's going to go through that control system, which we are developing. And then it will go to the actuators, and the actuators will then follow the given command to move the control surfaces, which will affect the aerodynamics ultimately. So actuators in dynamics and control field, actuators are equivalent to thinking controllability. That's the word. And sensors are equivalent to thinking observability for a system. Before even you design a controller for a system, you want to see if your system is controllable, as in, do you have enough actuators to capture or to influence the full state of a system? Then you will say, yes, the system is controllable, and you can actually design a controller to control it. If a system is not controllable, then you cannot design a controller to control it. Otherwise, it will become, it will not act predictably. Similarly, sensors help us to capture the data of all the states we are looking at. Therefore, if you have enough sensors to capture full state of the system, Then you say the system is observable, meaning you can observe the system completely in order to capture that output data and manipulate it. If not, then your system is not going to be observable. And these two concepts are important to design, heavier control algorithms outside, other than PID. And even with PID, you gotta have some kind of controllability with your system, right? So I'm gonna put this little picture to give you a glimpse of what I just talked about, fly-by-wire control loop. Let me put this picture here because why not? Let's see if I can fit it in there. So fly-by-wire control loop, that's how it goes. Pilot input goes to the flight control computers. Then it would go to the actuators, and then it will go to the aircraft control surfaces. And the loop is closed. So, you capture the response because you have enough sensors to capture them. Then the control surfaces send feedback sensors or send data to the feedback sensors, and feedback sensors take them back to the pilot input. So that's what we are trying to achieve. And let me see. Next thing is I want to show you just a snapshot of how many actuators you actually have in an airplane. So let me go into the pilot command subsystem because this is where we are going to work. And let me give you a glimpse of, if I can capture this guy. Let's see. Yeah, let me give you a glimpse of how many actuators. This is just a rough idea. This is not, it's just a representative picture. It doesn't tell the entire story. But even with this, you can see you have all these actuators here. The blue ones, the servos, which are controlling the control surfaces, are your actuators. And this is, there is a centralized flight control computer that commands all the actuators to move in a certain way, right? And therefore, it's important to know about to have actuator design inside of your model. So modeling actuators early in your design would be a smart decision, because that's how the engineers do in the industry. Because you do not want to realize that the controller you are designing works in simulation perfectly, but when you put it on a real aircraft, it does not, because real aircraft has actuators in them, and if you have not accounted for those, then it's definitely not gonna give you the same result as you see in simulations. But if you include Actuator Dynamics now, you are making your flight computer closer to how actual aerospace control engineers think about the system. So in real flight control projects, the actuator is considered as part of the plant, not an afterthought. That's one reason your simulator is starting to move from a simple aerodynamic model towards a genuine flight dynamics and control development environment, So again, let's start building it. Let's start putting the actuator first. And the way we will do that is over here for the pilot commands, del elevator. This is where I am going to put that. So I'm going to delete this wire, double click. We will get what is called transfer function block, right? So we are going to insert a function, therefore we need a transfer function block. So double click. If you just type transfer, you'll see it. This is the first block we put, and I'm going to connect both sides like that. Double click on the transfer function block. We are going to set the numerator to be 1 and denominator, let's do that 0.1 and 1. So I'll hit apply, and if I make this a little bit bigger, you can see the transfer function there. All right, so what I can do is I will put a scope here so we can capture if the block actually made a difference, So let me make this bigger, maybe zoom in. Okay, I want to put another scope to the input. So we want to see what is being input to the actuator and what is coming out of the actuator after the lag. So this is called a servo lag, and the function, I can put that there. So this is the function we are using. This is a first order system function, and in a first order system your key parameter is time constant. This tau here, the tau is a time constant, and the reason we want to use that is so that we can have a time delay, right, inserted into it, which means if my time delay represented by tau is less, that is a like my actuator is actually doing a good job of, you know, sending my command to the control surfaces faster, and vice versa. So let's start with 0.1, give that a try. Before we do that, let's make sure all of our pilot commands are 0 for now. Okay, that's good. These are all good. And yeah, everything else can stay as it is. Let's give that a run for like maybe 2 seconds. Okay. All right, let's check the scope. And you can see, so I'm gonna put the legend so we can, okay, the yellow one is my first signal, which is the output, and then the blue one is, okay, that's the input. So you can see how the input is the blue one, like the natural input which we used to have before we had this actuator dynamics, and after the actuator dynamics you can see the trend, how it's definitely influencing how your commands are going to the control surfaces. And this is where you are making like a realistic model, right? This is a very good representation of a realistic model. And let's keep moving on. So we want to do the same thing with rudder and aileron. For now, we are just going to design it, and like I said, as we are planning to put everything to FlightGear, we can, you know, look how good or how bad we want them to be over there and do the changes. Like we can come back and do the changes if need be. We can add more elements to it and things like that. So I am going to copy the transfer function block 3 times, as you see, and do the same thing there. And if you want, you can put a scope for all 3 of them and keep checking them, but I am good with this, so I'm gonna leave that as it is. And we can actually give a elevator deflection, like full aft elevator deflection of -25, and let's run that. And before I run that, I'm gonna turn off this simulation pacing, because you can see that little clock symbol. That means your pacing is on, which, you know, slows down the simulation. You want that when you actually want to do changes as the simulation is running, but otherwise really not. Okay, so let's get this scope one more time. Hopefully I captured that. Maximize. There we go. And I want to see that, okay, even with -25 elevator deflection, I am staying pretty good. It is converging, so that's a good thing. Okay, that looks good. Okay, so let's bring this back to 0. And all right, so that's a simple way you put your actuator dynamics into it. Very simple. Now, other things we can do is we can put rate limiters after the transfer function. After the actuator dynamics is designed, we can put rate limiters. What rate limiters do is they represent the minimum speed at which the surfaces, the control surface, can physically move. But so like if we later decide to create aggressive autopilots or very fast servos, then rate limits become important, because you can imagine, right, if your servos go too fast, you don't want them to move the control surfaces too fast. So we put like a limit to the rate at which the servos react or servos act. And then Yeah, so other things you can add when it comes to actuator dynamics and when your model becomes complex is like, dead bands, backlash, things like that. But for now, we will not worry about it. For now, we will just keep it as simple as we can before we actually go to the flight gear side of things. And so the real actuators, they introduce lag. So we saw the lag, right? We saw the lag on the scope. They have limits. So, if there are actuators flying the airplane, we want to account those limits into our design, and of course, bandwidth constraints. So that was that. And yeah, another concept is, like I mentioned, rate limiting, right? Rate limiting is a concept. If you want to answer a question as if, what is the maximum speed at which the actuator can move? Imagine an elevator can move like at 60 degrees per second, right? So that's the limit. So then even if a pilot instantly commands 0 degrees to 20 degrees, the elevator cannot teleport there. It must travel through all the intermediate positions, right? So that's like the concept behind rate limiting. Now, servo lag, as hopefully this is clear, servo lag is different from rate limiting. Servo lag is how quickly does the actuator want to respond, and rate limit is how quickly can the actuator physically is the actuator physically allowed to move, right? So you can have just the servo lag, which is what we are doing right now. You can have rate limiters to just the rate limiters to have a linear ramp response kind of thing, or you can have both to make more realistic and simple model. And a third concept is position limits. Now, position limits, we don't need to worry because we have already accounted for position limits when we are doing these things here. Speaking of which, I gotta make sure that I have all the right things. Looks like I need to change this one to negative 25 to 25 because can you guess why? Exactly, because these are in degrees and later they get converted to radians. So my earlier values were not consistent, and this is a good catch. Look at us, when we are testing things, we are actually seeing things. So let's try to run this one more time now that we changed the values, and make sure we have things as we want them. Okay, looks like the lag is still being shown, so that's a good sign. That's all I had about the actuator dynamics. It's really not a very complex thing. Again, you must understand the importance of it, but once you understand the physics behind it and why you need it, then it's easy to implement like that. Now let's go to the top level. What I would like us to do is actually get the outputs for all the things we were talking about. So I'm going to clean these up a little bit. Okay, that's good enough. Over here on this side, what I'm going to do is I will remove this scope for now and remove that scope as well. What we can do is take all of these and create a subsystem. There we go. We can make that bigger. Perfect. Bring that closer. I'm going to change the color of this block, so like that, and I will call this my flight. Let's call that our flight dynamics output. So outputs, there we go. Perfect. All right, let's see. So number 2 is XE, 3 is Euler angles. I'm gonna do one at a time. 2 is XE, 3 is Euler angles. Like I said, it's really useful to have things labeled. DCM VB WB. So this is DCM, which we are not using right now. So we will leave the terminator on. VB and W or omega B. Omega B. DCM is direction cosine matrix or direction cosine matrices. Sometimes, you know, we have multiple, but yeah, that's DCM for us. Number 2 is altitude. I will leave that there. I'm going to get rid of this tmux, and yeah, we can also get rid of that. Let me rotate it, Control plus R. That's perfect. And altitude, there we go. One thing is already set. Now I need to get a couple more output blocks. So there goes that. And I will start inserting them one by one. This is X, you know, position in earth frame, X position. Basically this is going to help us do the NED, northeast down convention. So X is pointing like north south direction, Y is your east west, and then this one is your altitude. You know, I need to just separate them out for a moment. Okay, looks like it got, you know what, let's see, altitude. Let me label them and then I will move them. Easy. And the name, you can always bring them, like you can change the position of these names like that. There we go. Nice. Okay, that looks better. Velocity relative to Earth. We can leave that for now. Yeah, I think I'll leave it, but I'll still put an output to it, and I'm going to maximize my room here. So I'm going to space these guys out a little bit more. Okay, another output. All right, that would do. And let's insert that here. Try that one more time. I can get rid of that for now. If I need it, I'll bring it back. This is velocity relative to Earth, so I can say VE. Sure, or V sub E. That can stay there for now. And I need to move these ones down because I need more inserting mux. Yeah, that can stay there. I need this mux. Copy, not like that. Try that again. Copy, paste. Perfect. So we want to separate all these signals out. Let's see, Control R, better. DCM, move down, and then these two will also be separated out, and omega will give us PQR, so that's going to be separated out like that. Okay, this is Control R. Okay, Control R, moving these away because we want to bring mux. Two more. Almost done. Okay. No bueno. There we go. That's much better. Okay. And perfect. All right, and a space bar will center them all or fit them to the screen. All right, let's get some more output. 3 for this. Okay, I think I've got enough. 1. Let's keep them like that, and then we will move. And that would be the last thing we do for this episode. All right, connecting 1, connecting 2, 3. Same thing here. And same thing here. That way we have all of our outputs coming independently, because like I said, we are going to work with these to put them on FlightGear. All right, let's keep naming them. So Euler angles will give you phi, theta, and psi. These will give us u, v, w, and finally we will have p, q, r. Sweet. Let's see. Now we can bring them closer if we would like. You can play with all of that. All right. Okay, so with that being said, let's make sure everything is aligned, because we do not want to have bad design. All right, and there we go. That is our output. And yes, we will stop here with this. We are going to play around with all these outputs to get a connection developed to the FlightGear. That's coming up. See you next time.